Can machine learning and AI make a difference in the fight against climate change? Where would we even get a global scale dataset that quantifies effects? How do we prepare and tease out insights? We're doing this and more in the CDP code tutorial today. Cities and corporations, large and small, are reassessing their long and short-term growth as the world recovers from a global pandemic. For communities to prosper and survive, there is a considerable focus on the sociological impact of climate change. The long-term perspective has made it more important than ever to look beyond and establish a sustainable future, one in which cities and corporations collaborate to assess, restore, and protect the environment. The Carbon Disclosure Project, a nonprofit organization, is trying to hasten an economic transformation that benefits both people and the environment in the long run. Investors, enterprises, cities, governments, and regions can use CDP's worldwide disclosure system to manage their environmental impacts on climate change, water security, and deforestation. The disclosure system keeps track of the thousands of corporations, cities, states, and regions that submit data as part of its annual reporting process and assigns ratings to companies and localities based on their progress towards environmental leadership. To monitor and manage their risks and opportunities, the world's economies look to CDP as the gold standard of environmental reporting, with the richest and most complete dataset on business and city action. With a growing national recognition of climate change's role in exacerbating the conditions that have resulted in earlier and longer seasons of destruction, now is the time to act and try new approaches. We at Amicus AI build on the tremendous body of work at the CDP, Unlocking Climate Solution Analytics Challenge. We'll have a link in the info box below. In particular, adapting the work from Man2 and Rebecca Verhese. Again, we'll link to their work. To center on corporate performance and what can be achieved with responsible business. We open source our code in a readable Jupyter Notebook format. More and more companies are going towards practices that are more environmentally and socially forward. As part of our research, we're looking for such companies that look to advance their financial benefits by using ESG metrics. To find these companies, we had to drop some of the initial metrics used in the Kaggle analysis. We found some of them not as useful. On top of that, we optimized the few metrics we decided to use. To make them more efficient in terms of what we are looking for, we included securities and financial metrics data. If you're still with us, please mash that like and subscribe button. You're on your way to being a more intelligent investor. All right, let's drop into the note. The CDP has simply done an amazing job combining both qualitative questionnaire data with economic data across countries and strata. First, we have our Python imports. Pandas, of course, is going to be instrumental, not just for a SQL, like E in the ETL, but for transformation functions that sit close to machine learning tools. For instance, GenSim is a classic natural language processing library which will quickly allow topic modeling. NLTK, which stands for Natural Language Toolkit, will provide handy NLP functions for instance, stop-word filtering, which means removing common English articles that clutter up and harm frequency-based statistical methods. Importing sklearn means that we're unlocking the path to machine learning functions. In this case, in preparation for an LDA approach, an ML-based partitioning method. The next cell reads in a host of Python tuples as a pairwise lookup for country and region codes. Some more complex compound names are normalized to easier handles. Cell 4, as we scroll down, launches into the loading aspect, which we can handle in memory with a reasonably powerful laptop. If I recall correctly, this data set was a few gigabytes, so most modern laptops can handle this fairly easily. What you have to do now is actually filter a lot of the CSV files, for instance, dealing with NAs, which means not a number or not applicable, and filling those with hopefully some sort of value. And so we build out our file structure to make it a little easier. We merge data, disclosing data with response data. We create a population data frame using the most recent values present in the disclosure data. We create a city location data frame to facilitate geoplotting. We fix some inverted coordinates. Possibly they've been switched around in their data entry. And then we can clean up all the temporary variables that we won't use in the end, just because the data set can get quite bulky if we multiply our in-memory store. Now we can load in the climate data reported by the corporations, which we have in this path we recommend you can use. And we read in the disclosure and response data again, merging the disclosure data with the responses. Oh, looks like we did that twice, actually. Furthermore, we load in the water security data. So they have a bunch of questionnaires that are just centered around water security. Water security and scarcity is known to be one of the most challenging topics in emerging regions, especially with increased heat and increased levels of drought. Water security is going to be very important in providing clean and sustainable living. We do a sort of similar cleanup as before. Then we load in human capital index data. So the amount of skilled labor, usually, that's available to companies and countries. We normalize the country names by the CDP values just to standardize everything all together. And we load in the corporate environmental impact. We clean the corporation names to facilitate matching with the CDP data. Next, we have the OECD Metropolitan GDP dataset. So this is going to be a lot of economic data. For instance, the gross domestic product, which is what GDP stands for. And that's going to do with all the commerce, all the transactions that occur in a country. Now, we can select the most recent data by extrapolating the max value for the year for each city. And that's a rough estimate. Then we can load in the per capita energy use. So this is something we'll dig into later, but many industries are more energy intensive than other ones, and this will affect their growth rate and their carbon footprint, of course. And then we do a similar thing to try and select the data for the most recent country. Then we also are very interested in how this affects quality of life, so we can read in the data associated with people without electricity and people with electricity access. So this is a survey types data set, loading their per capita electricity consumption data, the water consumption data, and then additional financial metrics for the organization. One of these metrics are operating income, which is the revenue minus cost of sold goods minus operating expenses, if you can recall from your most recent accounting class. We, again, are trying to just get the latest numbers, so we're going to grab the latest year's data for a given organization. And then finally, we're going to normalize data again, this time using the ISO mapping for that region. And this will get all our data sets in nice and neat fashion to process against all those different modalities that we loaded in. Now, finally, we can load in, again, some more extra data on the locations of the corporations, and then we clean up all the different organization names using RE, which is our regular expressions library in Python. And we're just cleaning up all those occurrences and replacing them with standard filler notation. And then we clean up further the locations as we did it in our previous approach. All right, on to cell 6. So we define a couple helper functions. So this helper function get cities will return values that are filtered by the city. Get climate is a similar effect where we query the data to return the climate change data, and then one to return the water security data. So that allows filtering the survey year and the question number and the column name. So these are nice ways that we'll be reusing over and over again to focus in on a certain question and modality, be it water, energy, or climate. Now, we might have mentioned our first analysis is going to be this topic modeling using IDF, TF-IDF versus latent Dirichlet allocation. So what we're doing is we're going to use a count vectorizer to find the n number of top words, and we're just going to build a topic model on those words. So a topic model is a statistical model of how often certain words belong to a topic, and then a topic is essentially a collection of a bag of words, and that's what constitutes a statistical definition of a topic. So we have these cities that are in different regions, in different languages that we standardize to the more English format. We start collecting our account vectorizer, and we make sure to remove all the stop words in actually English, Spanish, and French, just to be a little more careful. And then we train an LDA topic modeling. So that'll start to form these bags of words. And just using the sklearn package, we're really able to quickly do a one-liner, this LDA.fit_transform, in order to pull out the topic modeling data. So this function, get topic keywords, will add topic keywords to the a dictionary, which is a Python type, Python hash table type, and it'll load in the topics that are found in those groups of words. And we can further just join those groups of words and make that our sort of topic. And anything that contains others, will define that as an opportunity, because that's kind of the informal mapping. All right, so you can see that there are actually just a ton of qualitative terms, and so we define a data frame to map from these qualitative terms to standard topics. So if you have a opportunity that's in improved flood risk mitigation, we would map that to a flood mapping action. So just to collapse the dimensionality of some of these opportunities. In this cell, now we're looking at the top. We try to filter down this immense data set by the top 20 US cities. So we're taking a US domestic approach towards this view. And this is where we start using the pivot table functions, which allows us to filter on different categories in some of our data frames. So if you're very familiar with Excel type analysis with different worksheets, this is very similar. And what we do is that we have the different replacement values to map a natural language to label to a numerical label, and this will allow us to do mathematics with the different types of labels. Our next thing is we do pivot responses on columns and group as a list. So especially where there are multiple values provided, we can sort of just select a response and get those multiple values out. And we create numerical variables using the above replacement dictionaries. Again, this idea of trying to get things to a numerical format. So we separate columns for categories and hazards. We calculate exposure score for each risk. Then we add the values up by group using the group by function, which will do a kind of a reduce, which means a sum on the total city exposure. By defining replacement dictionaries for the following question on adaptation actions, this is again collapsing the dimensionality. We add a counter for tracking the number of actions undertaken. For all these self-reported actions, we sum them up. We aren't really too sure if one is more impactful, so we're taking this very normalized approach. We replace values for funding and the status of action with numerical weights. We count the number of co-benefited areas for specific actions. So this idea that is if it benefits multiple geographical areas, we make sure to count that, so you get sort of the extra credit for that. We look at the preparedness versus exposure for each climate hazard faced by a city, and we do that by grouping by the city group. We find the lowest vulnerability for a hazard can be 0, so we make sure that we kind of add a floor to this. And then we define the vulnerability. Adding to the city data frame, we do a group by this preparedness and the actions count. So we add these columns. We add this filtered pivot table column to our city data frame. Next, we calculate the count of each action and total number of associated co-benefits. And then we're going to join with the climate action opportunity. So anything that has shared columns, that have shared rows will be collected together. We calculate the opportunity payoff, and then we join with a vulnerability score for each climate hazard. We calculate the adaptation incentive for each hazard using vulnerability and opportunity payoff. So all this work is done to kind of tease out the aspect of how when a city or region takes an action, what kind of opportunity, what kind of reduction in vulnerability to climate change that nets them. Then we read in some of our S&P 500, so we're interested in the largest components of the U.S. economy, of the domestic U.S. economy. And then we see that this data set has some useful information on sector. We join the adaptation action data with city currency data frame to get exchange rates for each city. So there's also this often mentioned term on constant currency. So that's the idea that when you're trying to aggregate or compare different regions, you have to account for the currency exchange rate so that you have a weighted normalization factor, especially when you're looking at this. Makes the comparison of relative changes across a time period more accurate and effective. We calculate the average funding for adaptation initiatives to answer a question on adaptation actions. Again, creating a replacement dictionary for factors affecting adaptability. We indicate if this factor, we have these two questions that we want to tease out, impact and degree, if this supports or challenges. So this is the idea of turning a qualitative questionnaire into a quantitative factor that we can analyze. So we filter by these two question as a key in our data frame, and we pick out the numerical values from that. In order to calculate adaptability factor, we add the data for average funding for each city and for each human capital index score for countries. This inner join will drop cities for which data and adaptation actions funding is not available. So an inner join will only merge together data that belongs to columns that appear in both data frames that you're comparing. Let's only consider cities reporting at least some funding data. So there's going to be a reporting bias here that we should be aware of, but we're doing this in order to move forward with a relatively clean data set. And then this is actually a very important line, which is how we calculate adaptability. So this is sort of the payoff of all that data munging that was earlier in the notebook. So adaptability is going to be a simple formula of the adaptability factor multiplied by the actions content multiplied by a order of magnitude and the human capital index. Next, we calculate the city adaptability, and well, we're mainly just setting that to our last calculation. Now, what we're interested in economics usually is what's known as the marginal contribution, or the action at the periphery of the transactions. That means the buyers and sellers usually in a market, sort of where the rubber meets the road. The marginal contribution of a corporation to a city's adaptability. We add corporate human capital index scoring, merging by city, and it's to note this merge only works once, so once you do it, you're going to already have the factors, and if you try to merge again, it's going to have a conflict on this data frame, so that's something we should be aware of. Let me also state the reason why we're usually interested in the marginal contribution is because cities already exist. They have a long history. In economics, you're usually jumping in to a story in the middle of its telling. And so we're interested in how does a corporation's actions in the here and now affect the city's immediate future and what sort of impacts they're having on the city in the past year, and let that decide what impacts they'll have, and have our decision making decide what impacts they'll probably have in the next year, in the future. So marginal corporate adaptability. How do we tackle this problem? We've used the city adaptability index in the original analysis, and we've changed it to merge on the corporations based in the city. Thereby, we're inspecting the city adaptability that results from spending from corporate actors in that city. So that's what we're doing here. We're merging on the city using an inner joint again, and then we're making sure to drop any not numbers and grouping by the city and doing a sum. So what we're seeing here is New York City is at the top of the list on marginal corporate adaptability. They have done the best job in curating corporations to marshal them to their environmental impact. So I'm not surprised by this at all. New York City is home to some of the largest financial institutions and is also a fairly liberal city, so they're quite aware of this. It's a very well-off city, so they have the resources and the knowledge to tackle climate change and make sure that the environment that millions of people live in is the best environment that benefits every one of them. So one of the most important initiatives was from BlackRock, one of the largest institutional financial managers, recently had a large pivot to green investing and green resources. They actually got a lot of pushback on that because they are supposed to be passive custodians of people's funds. Usually they invest people's assets into categories that are passive vehicles known as index funds, sector funds. And so by voting those interests, they were seen as grabbing too much power and sway to affect corporate governance. And so they got a lot of pushback on that. They sort of further rolled out their technology such that they allow people to vote their shares, which is very forward-looking and seems like a natural democratic progression. But we have some more surprising cities, Indianapolis. And from Indianapolis, this also drops off quite rapidly. And then we can see some cities that may not have done as good a job. Houston, which is a large energy port known for its commercial sprawl, and Columbus, actually. So Columbus is an interesting factor. I'm not able to say exactly why they have such a large negative score, but that's something we can look into. Okay, the next topic, corporate liability, climate liability, and corporate performance. So the original analysis ranked organizations by their climate liability. However, this isn't quite the right analysis because there are linchpin energy organizations, energy intensive organizations, such as, for instance, the steel producing industry, which can use up to 10% of a country's energy usage. And they may or may not be punished in corporate performance. We ought to tie performance to climate liability, whether their actions are actually causing more climate damage, whether just because they're more downstream in the stack of producing the value chain, whether they're being penalized excessively for that. So first we again try to take these natural language labels to quantitative labels, and we replace fields with numerical values. We do the constant currency exchange normalization, and then we have the original sort of analysis is the cost of the response plus the minimum potential financial impact. So that's the financial cost to them. We calculate the liability factor, which is the magnitude times the likelihood times the time frame, and then the climate liability, which is the financial impact times the liability factor. And then we add all the values for a company, and we ignore companies with no costs reported. So there's again a reporting bias. We add revenue and earnings data for these organizations. Here we also pull out the performance of the company in a given year. So we're trying to understand how their environmental actions are being made in light of their corporate performance. We do some fuzzy matching such that we're able to group together different companies that fall under different names. We do, again, a clean and merge on the companies. And then finally, we're able to do a statistical analysis where we try to correlate different labels and how they correlate with high scores on, for instance, climate liability. So climate liability tends to correlate, if we want to look on the first column, tends to correlate with high total environmental costs. It doesn't actually seem to affect revenue that strongly, operating income that strongly, the comparable performance, or the return. That seems to be merely negligible. If we want to look at, for instance, what most affects the return, we would see that the compensation is one of the most important factors. All right, so now we move on to corporate risk mapping. And then we again do a dimensionality collapse into aspects such as water stress, mass movement, biological hazards, drought, energy supply issues. And then we map the risk to the corporate risk, or the environmental risk, really, because corporations are affected by the environment. So these two elements we don't actually look at. I think that was, we're actually interested in the analysis of corporate electricity greed. So in this analysis, we're adding the operational expenditure, the OPEX, and operational efficiency, the OPEX over profit, as possible indicators of frivolous energy use. The idea is that large OPEX might mean that they're spending wastefully, but more precisely, if they have large OPEX over profit, they're spending a lot of money for a given level of profit, which means that that could be wasteful. So we can look at, we're going to filter by the primary industry. We're looking at emission data and calculating the mean by the industry. So we're going to use that to level out industry level effects. The idea is you want an apples to apples comparison. So we're hopefully comparing companies in the same industry. We load the corporate energy use data. We select the data relevant to electricity consumption, joining with the organizational revenues and earnings. So revenue is known as the top line. That's the total number of income, cash they receive, and then earnings subtracts off the costs associated with that revenue. We're converting to the float format, dropping corporations with no reportings again. And then we're considering only corporate reporting at least some energy consumption. We're converting the per capita consumption to megawatt hours, just to go down 3 orders of magnitude. Calculating the electricity greed by dividing corporate consumption by electricity poverty. So electricity poverty is the global per capita consumption multiplied by the people without electricity. So the more people without electricity, the more electricity poverty there is in a region. And then we're going to merge that with the corporate data and again pull out some relevant correlations. So to answer the question, we look at operational efficiency. So we see operational efficiency is correlated with return in the year, the corporate performance, the stock return, and the earnings before interest and tax. So those are the two most relevant things. In terms of energy greed, we find that the largest correlation is with compensation, and there's less correlation with the return, and there's also a slight inverse correlation with operational efficiency. So more greedy companies may be more inefficient, which is a natural correlation, but it's not a terribly strong correlation, not as strong as the correlation you'd have between efficiency and returns. So we found that negative correlation between operational efficiency and energy use. This would be aligned with shareholders and the public, people who are environmentalists. So a natural way might be to weight the operational efficiency larger and have that affect the energy use more in terms of a policy standpoint. Next, we look at the average deaths per terawatt of energy generation. So there's this idea that if there is more carbon being released, this usually correlates with dirtier industries, and such carbon generation affects the respiratory health of many people. It can lead to environmental pollution in the areas that people are living, which may lead to increased risks of serious and persistent diseases that reduce lifespan. So mapping the top fuels by use, we collapse biofuels to biogas, methane, ethanol to biofuels. Different types of coal, we try to group them: brown coal versus more thermal and thermal commercial coal. Different types of oil and the different grades, we collapse for simplicity. Now we query the fuel use by the corporations, and we do some additional standardization. We join the fuel category with fuel deaths, and we calculate the number of the deaths by multiplying the terawatt hour of fuel consumed times the death per terawatt hour. Pretty straightforward. We can do this again with the fuels that are linked in the water consumption data set, and we query city response data on collaborations, replacing all self-defined categories with others. We do this again on a different collaboration data set. Actually, we've just done this twice. So we use the collaboration strength and tie it to corporate performance to answer whether cities that work with their resident corporations yield a business synergy. So we get corporate climate risk data. We also do it the same with water. We standardize some of the columns. We combine the two data frames. We do more risk mapping to standardize the term, collapse the dimensionality. And then we get the corporate data on reduction initiatives, and we select relevant data to the initiative category and type. We convert the costs to standardize on the US dollar, and this is, again, since we're in the domestic calculation, this is less of an issue. And we calculate the lifetime score, which is the estimated annual savings times the lifetime times the minus the investment amount. The / there is just a formatting code notation. We query city data on emission reduction actions, create a data frame joining the corporate initiatives with the cities that they're headquartered in. So the next aspect is that there's a little bit of machine learning, which is defining a word-to-vec model. So word-to-vec is an early machine learning model from around 2015 that just uses high-dimensional embedding. So an embedding is a vector, say a list of 128 floating point numbers. So floating point numbers is a standard computer science format that has a vast range exceeding hundreds of millions of different values. And so in this 128 dimensional space, you're able to have a rich embedding space to have concepts that are related to each other and understand how concepts are far apart from each other in a mathematical distance schema. So we make sure to cap out the distances in our words in our embedding space. So between the different topics in the model, we calculate a word mover's distance. The word mover's distance means that for each word in the topic model, so I mentioned this earlier, is that a topic model is a collection, is a basket of words. What we're doing is we're calculating a distance between two distributions, two baskets of words. And we're able, it's inspired from this idea of earth movers distance. So if you can imagine two hills, two probability distributions that are, for instance, a smaller hill and a bigger hill, if you had to move the area under that curve, so this is going back to your high school calculus, you can slowly remove 1 grain of mass from one mound of dirt to the other mound of dirt. So that's called the earth mover's distance. And what is the minimum distance you need to move the dirt from one mound to the other mound? And so we think of that, we can apply that more abstractly to the word mover's distance, which is a probability distribution based on the word to vec representation of the words. So by doing that, we finally are able to get a collaboration strength. So we say the collaboration strength is the zero score, the mean of the word mover's distance score grouped by the cities and organizations subtracted by from a normalization factor, gives us the zero score, which is this environmental response score. And we calculate the strength by using the shared risk times the opportunities. We sort the values by this collaboration strength, and then we drop the not numbers, and then we merge this on our corporate data to again get a correlation. So what we're seeing here is that shared risks, for instance, most correlates with compensation and collaboration strength. So that's pretty well understood, is that if there is a strong collaboration strength, it's because they have strong shared risks. For this topic modeling, this environmental response score is, again, the words they use to describe and the topics they focus on and the ones that they're responding to has a high correlation. If they're responding to these environmental effects, has a high correlation with collaboration strength. So they're both focusing on the same topics. This is not surprising. And then how do we look at this with our financial metrics? So if we read across this operational efficiency metric, which continues to be an interesting one, if we look particularly at the zero score and the collaboration strength, it seems to be a more ambiguous type of determination. And that is our final analysis using topic modeling. So we did find that companies that focus on the same environmental topics tend to have strong collaboration strength with the cities that they're domiciled in. So to some degree, there's some degree of correlation where corporations try to be good tenants of their cities. There's an additional philosophical debate where we know that companies to some degree consist of the people that live and work of them. Of course, this is not strictly true because most corporations are very hierarchical. And then they also have to answer to outside interests such as their shareholders. But the data and the survey from the CDP seems to indicate that there is some level of shared destiny. All right, so that was a lot of data munging and a tad bit of machine learning in our overview of the CDP data, which we tried to tie more strongly into corporate performance and corporate financial metrics. With this overview, you've hopefully gotten a better handle on climate change and how corporate actors view climate change and what they're doing about it and how it affects the cities that we live and make our homes in. If you want this content and more, please subscribe and like this video. Happy intelligent investing. Thank you.